Hello everyone, my name is Kyle, and today we're going to be building this cool VDB falloff effect in Houdini. We're going to explore some simple procedural modeling setups, as well as how to create this mapped falloff throughout a VDB so we can eventually create this transition. So let's jump into Houdini and create this thing. Okay, so the first thing we want to do is drop a geometry container. Never been done before, very, very difficult stuff. We're going to create a 2. Let's keep this at 12 columns and increase the height to 2. I'm going to keep this at the center of the scene, and if we turn on the grid here, you can see it's kind of in the middle, so I'm going to drop down a match size to make sure it sits on the floor. Let's drop down a primitive wrangle and write a little bit of code. Let's write add point on the incoming geometry on VFP and remove prim. 0 on every prim num, and let's put a 1 at the end. And this should add a single point in the middle of every single prim on this column here. We're going to use this to copy some geometry and eventually boolean out those holes we saw in the initial reference. So let's do that. One thing we will need to do before we do that, though, is create some normals. And the problem is, we can't put a normal stop right here. And these points won't get these normals because these points don't exist before this chain. So we're going to need to use another attribute wrangle here. And this one's just going to be a normal point wrangle. We're going to plug in the first one here and the second one here. The normal is going into the second input. And we're going to write a little bit of vex. Let's initialize 2 attributes. Let's do vector UV. Spell it correctly. And integer prim. This is for the function xyz dist. On the current geometry, or I'm sorry, the second input geometry, we're going to use the current origin geometry. And we're going to write out to those 2 attributes we just created, prim and UV. Then we're going to grab n using a prim UV function. From the second incoming geometry, we want n, and we're going to use the prim and UV that xyz dist created. So this is what the code is. I'll make that a little bit bigger. And now if we middle click this and click the normals, you can see that these points are inheriting the normals from each primitive, which I think is some cool vex. So we'll just drop a null here. And I'll name this get normals. The reason you would want to use xyz dist and prim UV in this scenario is because, usually you think you could just use an attribute transfer here, right? And I want to transfer the normals from my original geometry onto the new geometry. Let's make these point normals. But you can see if I top-down view this, the normals aren't lining up or transferring how you would think they would. So this way they line up perfectly. Now we need to copy some geometry onto these points, and then we're going to boolean it out from this original geometry. So let's start by just copying lines. I'm going to do a copy to points. You can see they're also not lined up in the middle, so what we can do is a match size. And here you can just tweak the height to roughly match, what's going on here. And the reason we set up those normals is because we can drop down a sweep node now, and we're going to pipe this in before the copy to points. It's giving an error because we need to define what the surface shape is. So let's just put a ribbon for now. And the cool thing about the ribbon is with these end caps, you can select grid, and it kind of creates, let me turn off this visualization. It creates this arc, And we're going to use this with a poly extrude, P extrude. Let's output the back. And if you're getting this weird kind of blue visualization, that means the normals are reversed. So we're going to use a reverse stop to change that. We're going to use this ribbon copied along the points. And if we, I could turn off the get normal attribute wrangle, and you could see kind of what the normals are doing with the copy to points. They're lining basically all the pieces up on the faces of this initial tube. Not that guy, this guy. But they're oriented in the wrong direction. So let's just drop down to transform stop after the reverse. And I think this should be in Y by 90. Yes, that looks good. And right now they're lining up just on the very edge. So let's shift that in a little bit. This is often a guessing game for me. Yeah. There we go. Let's grab our original normal geometry. I'm going to create another null here just to organize our network a little bit. Make this a little bit easier to see. Let's take this null, and we're going to do a Boolean subtract here. Well, first let's extrude this tube. I think I want to extrude it inwards. You could also extrude it outwards. But for this, let's do inward. I have the same problem as I did on the sweep with the reverse normals, so let's reverse those. And plug these two into the Boolean. So now we kind of get this shape. And I think that's looking pretty cool. We could increase the height of the line to kind of help with that. I'm going to decrease the width of this to give us a little bit more room in the geometry. And this is all up to you, If you get this weird error, it's because the length of the cutting geometry isn't as long as the tubes extrude. So let's mess around with this a little bit. And I feel like that's in a pretty good spot. One thing we may want to do is I'm going to copy and paste this tube. I'm actually going to delete this and do Control-Alt-Shift. So we're going to create a reference copy. So all the parameters are the same. And the reason I want to do this is, let's see, if we plug it in here, we also need to match size, which I'm just going to copy and paste. Is I want to increase the resolution on the y-axis. So once we Boolean this, we can do something like a twist. Plug that in here. It's oriented in the wrong direction. It's always oriented in the wrong direction. We could plug in a twist at the end, increase the capture length, and now we have this kind of cool twisting geometry. Whereas, I think if I was using the original geometry here, you may not get the best results because Houdini doesn't have enough points to actually deform. So cool. We have this weird spirally looking piece of geometry. It's kind of a fun procedural modeling exercise. And we'll just call this in geo. We'll reference this later when it comes to shading. Okay. So now we need to work on the fall-off transition that kind of moves up through the geometry. And the first thing I'm going to do for this is do a points from volume stop. So let's drop that down. There aren't nearly enough points in here, so let's drop the separation down to like 0.05 maybe, even lower than that. 1. That's probably too much, so let's do 2. Feels about right. And here we're going to create a map attribute. And when I say map, I mean we want this kind of 0 to 1 gradient moving throughout the whole object. And the 0 to 1 gradient is what's going to control this mask that we're going to create later on. So let's create this from a bounding box. Let's write vector vbox is equal to rel point vbox on this incoming input. on position. And then we're going to create our map attribute. f@map is equal to channel ramp. And this is just in case we want to edit it later. Call this ramp. And we're going to run this over bbox.y, the y part of the bbox vector. So if we middle click this, nothing shows up because we have to create our channel ramp. And there we go. So now we have this 0 to 1 ramp going through the object. The next piece of code is something I learned from my colleague Mark Fancher. I'm going to link to the video right now. It is one of the best Houdini tutorials you can watch. It totally changed how I think about Houdini and how I create a lot of these fall-off effects. You know, if you're working in Houdini, you are going to be creating a lot of these transition fall-off effects. So I definitely recommend checking out this original video. But I'm going to write a little bit of Vex code here that he explains very thoroughly in his video, but I'll just write it out here. So the first thing we need to do is read in our map attribute that we just created with the bounding box, and we'll do that with float map is equal to f.map. And then we're going to initialize two attributes here, two local variables, I mean. Let's do float p is equal to channel float position. And float w is equal to channel float width. The next thing we want to do is fit p. So let's write float mask is equal to fit p. Or actually, we don't want to fit p. We want to fit map from p to p plus w between 0 and 1. And then lastly, we're just going to write this out to an attribute called mask. So let's see what this does. We have this new mask attribute. And as you can see, if we scrub through this position channel flow, we have this very lightweight, super controllable way to control fall-offs. And this is just super, super powerful because no longer do we have to rely on simulation or rerunning simulation or anything like that to create fall-offs in Houdini. We can just create this normalized map. And then with this normalized map, create a mask. Two extra little key features are before the first fit, you can see down here when the position is at 0, there's still a part of the mask showing. So we're going to do a fit before this. We'll do p is equal to fit 01, p from negative w to 1. And that should get rid of that initial bump there. And then lastly, just for some more control, we're going to do float mask is equal to, or we don't have to rewrite it. We could just do mask is equal to channel ramp. We'll call this shape of mask. So if I do this, now we can reverse it. We could really kind of shape what it looks like in that 0 to 1 area down here. So cool, this is the basis of the effect. We're going to call this map transition. And we're going to call this create map. I'm going to shade this blue because really this is the only node we need to animate in this entire setup. Just this position value. Another cool way to edit kind of these map transitions is if we run a noise through this initial map. So right now, this mapped transition is looking at this map attribute, and it's fitting it as we scale this position slider. But we can abuse this by editing this initial map, this normalized 0 to 1 map. So let's create an attribute VOP. We're going to need a few things in here. Let's drop down an AA noise. We're also going to fit this AA noise, and then we're going to eventually ramp parameter. And then let's bind, export it out to an attribute. So let's plug these in. P goes into the A noise. For the fit, I'm going to just put this at like negative 0.5 to 0.5 from 0 to 1. The ramp, we'll switch that to a spline ramp. And we'll export this as, let's just say, noise. And then to, actually combine the map we were making into this noise, we'll do a bind import like this. Call this map. And we're going to multiply this against our noise. And we could actually bind export this into map. Oh, one last thing we want to do is right-click on the A noise, vex VOP options, and create input parameters. That just promotes these parameters up to this level. So let's plug this in. Let's turn on noise and turn on our ramp. So right now it's way too big, but if we kind of increase the frequency here, you can see that we're adding noise to this map. Turn on the map. You can edit the values with the channel ramp, make it less rough. You could do this forever. But now if we plug in this, we'll call this create or add noise to map. Now if we looked at the map transition, the mask is a little more irregular, which I think is a nice touch. You can increase the width here. That's feeling pretty good to me. But right now, this is just points, and we need to turn it into geometry. So the way we're going to do this is through a VDB from particles. And the VDB from particles, right now, if I make sure you have this turned on for shading, or else you won't see the VDB. Default settings are not very good. So a couple things we need to do is reduce this minimum radius way down. We also want to make this voxel size roughly the same as this particle separation. So what I'm going to do is just copy this parameter and paste it into voxel size. And that may have been a mistake. I'm gonna delete this channel actually. And I'm just gonna put this at like 0.5 for now. And the point radius scale, we need to decrease quite a bit here. Now you can kind of see that original shape we had. Wonder. Yeah, we could probably keep the point radius scale at 0.02. That makes sense. Let's increase the VDB resolution. And honestly, this doesn't need to be super precise because what we're going to do at the end of this is do a VDB intersect, so it actually cleans up a lot of the edges. But for now, we just want the rough shape. And how we're going to drive the fall off is VDB from particles actually reads in the p-scale attribute like a copy to points. So if we just drop down attribute wrangle real quick, we're going to write out this, we're going to say, create p-scale. We're going to write out this p-scale attribute in f at p-scale is equal to channel float. Just call this p-scale. And then we're going to multiply this against, so times equal, our f at mask that we just created. So let's create this, put this at 1. And if I now select this and we move through our map transition, you can start to see what this is going to look like. So this is obviously still too low resolution. Maybe we need some more points. 0.5. 2. 1. So that's getting closer. Now this is getting a little heavier. But you like right before render, you could ramp up the resolution and just send it. Okay, so I'm going to leave it at this midpoint right now. To help kind of shape this a little bit better, I'm going to do a VDB reshape. and we're going to use the dilate operation to blow it up a little bit. And then we're going to go back up to this original null. Oops. Create a VDB from polygons. Let's do 0.01. This one should be pretty high resolution. And a VDB intersect. So this is, before the VDB intersect, and this is afterwards, and we get much cleaner geometry this way. Lastly, we want to convert this. So let's do VDB convert polygons. And if we had UVs, for example, I'm just going to throw a quick UV unwrap. Obviously, these are going to be really messy UVs. This one. If we had UVs on our object, what we could do is just at the very end here, I'm going to Control-Shift-V, just object merge in the node I just selected. I'm basically doing Control-C here, and then object merge, Control-V. We can transfer these onto our new converted VDB. Let's turn off points and primitives and turn on vertices. All we want is UV. And we can also grab a few other attributes this way, right? And this you could use for shading if you're using Redshift or Karma or anything like that. So what we want to do is, I believe the attributes are coming out of here. This is kind of a cool visualization. I'm just going to create a null to reference. We'll call this out, mask, and map. Color black, Control-C, Control-Shift-V. So this is getting the UVs. Get UVs. And we're going to attribute transfer. You do want to be a little careful with these attribute transfers, because if they are running on a time dependency, these guys tend to be really heavy. But for this setup, I think it's lightweight enough. We don't want to transfer any primitive attributes, and we want to transfer mask and map. If you don't have any attributes selected, it'll transfer everything, but in the past, I've had issues where some weird things happen if you don't really declare what attributes you want to transfer. So now, this is the new VDB converted geometry. We have these attributes to use and edit. Real quick, in this map transition, let's go from 0 to 72 here. I'm just going to do 2 quick keyframes. And I'm going to just make them linear. So this is pretty heavy right now. One thing with this setup is you don't want to turn on adaptivity on the VDB convert, because we're transferring over attributes to the points. So although it's heavy, I recommend not turning on adaptivity for this. If you don't like some of these, rough VDB edges, what you can do is some VDB smooth SDF right after the intersect. And that'll get rid of a lot of those. It'll also make, the entire mesh a little more mushy, but it's kind of just an artistic fine-tuning here. Of all the operations, I think mean curvature flow is probably the least destructive of all of them. Maybe Laplacian. I think that's how you pronounce that. Laplace. And that's pretty much it for this effect. So if we just highlight this, call it out VDB point transition. If I frame this just real quick, let's launch a quick flipbook and see what it looks like. So the flipbook finished with, about a minute of cooking. The network is getting pretty heavy right now. And, I think it's really just a push-pull of changing the point density and the VDB resolution. But this is what the effects is looking like. And you can use this mask attribute that's being visualized right now in any render engine to, you know, kind of blend between materials, which is what I was doing earlier. But I think rendering is a bit beyond the scope of this tutorial. If you guys are interested in that, I can do that in a future tutorial. But I hope you learned something in this, and I'll see you guys in the next one. Thanks.